Welcome back. In this video, we continue our study of Chapter 2, and we will cover the first half of Section 2.2, which is about the geometric forms of the Hahn-Banach theorem. Okay, so let us first start with a simple problem. In the plane, if we have two disjoint convex sets A and B, is it always possible to separate them by a line so that each of them lie in a different half plane, like this? Of course, intuitively, at least, we expect that. But any proof actually, is a little bit difficult. So it's not a trivial fact. And we can, now, why do we need convexity? Because if one of the sets is not convex, even in the simplest setting of the plane, there's no hope of separating them with a line, as you may see in this picture. So convexity is a necessary condition, actually. Okay, now, and we can ask a similar question in R3. Given two convex disjoint sets of the space, can we separate them with a plane, so with a two-dimensional space, so that each of them lies in one half space? Okay, now I'll not draw a figure, but you can draw this. So, and we would like to, so intuitively, we expect this kind of results. But let us try to formulate a little bit more general problem. And it's not clear yet how to formulate this problem in higher dimensions or even in infinite dimensions. So let us try to capture the idea, how to generalize the notion of a line in the plane or a plane in the space, how to extend this notion. Okay, so first of all, observe that if you are working in the plane, the equation of a line is something of the form a1x1 plus a2x2 equal alpha, or if you like, a1x plus a2y equal alpha, if the coordinates of a point are x and y. Here the coordinates are x1 and x2. Okay, so, and of course the coefficients a1 and a2 should not vanish at the same time. So here actually I meant a1, a2 is not 0. Okay, not so one of them could be 0 actually. If a1 is 0, then this is just a a horizontal line. If a2 is 0, then this is a horizontal line. Okay, so the coefficients do not vanish at the same time. So this function of x1, x2 is not trivial. It's not the 0 function. Okay, so here actually I meant the product. a1, a2 is not 0. Okay, so now the function of two variables from R2 to R given by this formula. So here, of course, a1 and a2 are constants. So this is a linear map, actually, from R2 to R. And by the way, the adjective linear comes precisely from this analogy. Why do we call it linear? Because it resembles the equation of a line. Okay, so we have, yeah, so this is the condition a1, a2. So this function actually is not trivial. It's not the 0 map. Okay, and such a line divides the plane into two regions or two half planes. The set of points of coordinates x1, x2 such that f of x1, x2 is less or equal than alpha, and the other part, bigger or equal than alpha. Okay, so this is what we call half planes in this case. Okay, so this is actually a good starting point. And if you are working in space, the equation of a plane is something of the form a1x1 plus a2x2 plus a3x3 equal alpha, where alpha is a number. So once again, this function of x1, x2, x3 is linear in the triple x1, x2, x3. Okay, and of course not trivial, because not all the coefficients of the plane should be 0, because otherwise we get, so if alpha is 0, we get everything. And if alpha is not 0, this is empty. Okay, so we are excluding these cases. Okay, so now we have an idea actually that defines the notion of, or the analog of a line in plane and a plane in space. So this is the general definition. a line in the plane and a plane in three-dimensional space are what we call affine hyperplanes, or just hyperplanes. Now, what is the difference? A line need not be a subspace because it need not pass through the origin. So, okay. So in principle, we should call a line an affine hyperplane, but in practice, it should be clear from the context. Okay, so in general, an affine hyperplane of a vector space E is a subset of this form. Okay, it's the inverse image under a linear map, non-trivial linear map of some singleton alpha, some constant alpha. So it's the set of points in the vector space whose image under F is exactly equal to some, if you like, a level set alpha. Okay, alpha is given here. So a hyperplane or an affine hyperplane is characterized by two things: a linear form or a linear functional, if you like, which is not zero identically, because if F is zero identity, we saw what happens. We either get the whole space or the empty set, and this is not a hyperplane. So a hyperplane is denoted by this symbol. So actually, we can write it f minus 1 of alpha. Here, actually, we should write f minus 1 of the singleton alpha, but for simplicity, we can write it in this way. So, and another notation is f equal alpha between brackets. So this precises what is the linear map and what is the constant. Okay. So our starting examples were just particular case of this general definition. Okay. Okay, so before we formulate the problem of separating convex sets in the general context of normed spaces, we have to learn some basic things about affine hyperplanes. Okay. So this is what we are going to do in this part. Okay, so the first result, if we have a non-trivial vector space E and a non-trivial linear form F and a real number alpha, then the following hold. The hyperplane F equal alpha is the translate of the kernel of F. So we can write it as x0 plus the kernel of F. Kernel of F is just F minus 1 of 0. So it's the set of points x such that F vanishes at this point. This is actually trivial to prove. It's not difficult, and maybe you encountered this in algebra. Here, I don't put any norm, just the setting is algebraic. And the second point is that the kernel has co-dimension 1, and this is something that we expect, actually, because a line in the plane has co-dimension 1. So an algebraic complement is another line, which is not parallel to it. And the codimension of a plane in three-dimensional space is also 1. But this is a very general fact. Okay, so the first point, let us prove that a non-trivial linear functional is always surjective. So there's always a point, so it's not empty actually, this is the meaning. Okay, so a hyperplane is never empty. Okay, so pick an element alpha in R, and our assumption that f is not the zero function. So it means that there is at least one point at which f does not vanish. Okay. So take now x0 to be alpha over f of a, which is, so we can divide by f of a because it's not 0. So this is a constant. This is a real number multiplied by the vector a. Okay, so a is a vector in the vector space, and alpha over f of a is a real number. So x0 is a multiple of a. So if you like, x0 lies in the subspace generated by a, which is one-dimensional. Then if you apply f to both sides, you get f of x0 equal f of alpha over f of a times f of a. So f of a over f of a cancels, so we get alpha. Okay. By linearity. We can put the alpha outside. Okay, so the hyperplane is never empty. Now, what does it mean to say that x is in the hyperplane f equal alpha? It means that f of x equal alpha, but alpha equal f of x 0, so f of x equal f of x 0. And by linearity, this means that f of the difference is 0 by linearity. So this means that x minus x 0 belongs to the kernel of f. So x belongs to x 0 plus the kernel. Okay, so this is really trivial, and in principle, you encounter such reasonings in a course in algebra. Okay, so next point, why the kernel? How do we know that the kernel has codimension 1? So we have to find an algebraic complement of dimension 1. Okay, we use this standard trick. We write x as x minus f of x over f of a times a plus the same thing. And now we look at the first term, x minus this multiple of a. So we call the first term x1 and the second term x2. Now, if it's easy to check that f of x1, f of this term, is just f of x minus f of x times f of a over f of a, so it's just 0. And x2 is just a multiple of a, so it belongs to the subspace, the one-dimensional subspace generated by a, that we denote by Ra, as you know, or if you like, a between brackets, or vect a, if you like. Okay, so this is the first condition. And second condition, the intersection of the kernel with this line, if you like, because this is a line in E, is of course trivial. Very easy to check. So we can write E as the direct sum. Here it's the algebraic direct sum, not the topological, because there's no norm here. So this is really a lemma in algebra, if you like. So we can write E as the direct sum of the kernel of f plus this one-dimensional space. So this precisely means that the codimension of the kernel is 1, because the dimension of Ra is just 1. Okay. So this concludes this proposition or lemma, if you like. And now we can actually prove a kind of converse. Any subspace of codimension 1 is the kernel of a linear function. Of course, not trivial. So try to prove the converse. Okay, so it's an interesting result in algebra. I will not prove it. You think of it a little bit, okay, just as a warm up. Okay. Okay. Now we move to norm space. Now we put a norm on the vector space. Okay. So we would like to deal with linear continuous maps. And if the linear map is defining the hyperplane is continuous, then as we know, since the hyperplane is the inverse image of alpha under f, and the singleton alpha is closed, then the hyperplane corresponding to a continuous linear map is automatically closed. Because it's the inverse image under a continuous map of closed set. Okay, but as we know that in infinite dimensions, not every linear map is continuous. In finite dimensions, this is the case. Okay, so we'd like now to see when a hyperplane is closed or not. And it turns out that a hyperplane is closed if and only if the linear map defining it is continuous. Okay, now one way is easy, as you observed, because a hyperplane is the inverse image of a singleton. And now suppose that the hyperplane is closed, and we reason by contradiction. So suppose that the hyperplane is closed, but the map, the linear form defining it, is not continuous. We know that if a linear map is not continuous, then it's not continuous at 0, because there's an equivalence between the two. What does it mean that f is not continuous at 0? It means that there exists a sequence xn converging to 0 whose image under f does not converge to 0. Okay, this is just sequential continuity because you are working in a metric space. Okay, what does it mean that f of xn does not converge to 0? If you write the definition, if you negate the definition of convergence, you will convince yourself that this implies that there is a subsequence x and k whose image under f in absolute value is bigger than a positive constant epsilon. Okay, so epsilon is not ours given. I think we did such reasoning before. It's really standard. And now, instead of working with subscripts, what we usually do to simplify the writing is to still denote the sequence by the same symbol. Or you can change the symbol. You can write yn, if you like, instead of xn. Okay, so this follows from the negation of the convergence condition in terms of epsilon and delta. Okay. So you have to negate for every epsilon that exists and 0, etc. You negate it, you'll get that. Okay, so now we set yn equal xn over f of xn, but we understand that actually this is a subsequence of the original sequence. But it doesn't really matter, actually. Now, if you take the norm, you'll get norm of xn over absolute of f of xn, because here xn is a vector and f of xn is a number. But since f of xn is bigger than epsilon, then 1 over the absolute value of f of xn is less than 1 over epsilon, so the norm of yn is less or equal than 1 over epsilon xn, and therefore yn tends to 0 because xn tends to 0. Okay, so this is... And if you apply f to yn by linearity, you'll get f of xn over itself, so you get 1. And now we choose an element z at which f does not vanish. And of course, this is possible because f is not trivial. Or you can just take z equal y1 if you like, because f of y1 is 1, so it's not 0, or any term of the sequence. Okay, so fix this element z in E, and it satisfies that, so z is not in the kernel if you like. Okay? And now consider this sequence, zn equals z, this constant, minus the image of z, which is different from 0, could be equal to 1, doesn't matter, times yn. Yn tends to 0, and z is fixed in this reasoning. So as n tends to infinity, zn converges to z. But if you apply f to this equation, you get f of zn equal f of z minus f of z times f of yn. So you get f of z minus f of z, so it's 0. So actually zn is in the kernel, but it converges actually to z. But the kernel is closed, and this is a contradiction. So from one hand, we should get z is in the kernel, but actually we know that f of z, our choice of f of z, means that z is not in the kernel. So this is a contradiction, actually. Okay? Therefore, our assumption was wrong. Okay? So the kernel is closed. The kernel is closed, therefore any translate of it is closed, because translations are homeomorphisms. Okay? And there is an interesting result, actually. What happens if f is not continuous? If f is not continuous, so not only its kernel is not closed, but actually we can prove that it's dense. Okay? And this is something particular to infinite dimensional spaces, because if E is finite dimensional, then any f is continuous, actually. Okay? So the only case where f is not continuous is where E is infinite dimensional. So this is something really particular to infinite dimensional norm spaces. Okay? We can find a proper subspace of E which is dense. Okay? This cannot happen in finite dimensions. Okay, so this concludes our two basic results about hyperplanes and kernels of linear maps. And now we can, having said this, we can formulate our problem. So in general, we can give the definition of separation of two convex sets, or just two sets actually, because this is just a definition. In a very general context, if you have a vector space E and two subsets A and B of E, we don't assume that they are convex. We say that the hyperplane f equal alpha separates A and B if f of x is less or equal than alpha for every x in A, and f of x is bigger or equal than alpha for every x in B. Okay? This is the precise definition. And here I just, when I say nothing, I just use the term separates. Okay, so this contains this situation as a particular case. So the two sets can be tangent. Okay, and in this case, the separating hyperplane touches, of course, if they are disjoint, so one of them, so we exclude the boundary. Okay, if we want them to be disjoint. Okay, but I didn't assume that A and B are disjoint. Okay, so. But they could be tangent. So this is just normal separation, or separation in the ordinary sense. Now there is a stronger notion of separation, which is strict separation. So we say that the hyperplane f equal alpha strictly separates A and B if there exists a positive number epsilon such that f of x is less or equal than alpha minus epsilon for all x in A, and we have the reverse. So f of x is bigger or equal than alpha plus epsilon for every x in B. So we have a situation like this. Okay. So here, this illustrates the fact that this hyperplane separates strictly the two sets because A lies in the half space f is less or equal than alpha minus epsilon, and B lies in the half space f bigger or equal than alpha plus epsilon. Okay, so there's some distance between A and B. This is strict separation. Okay. So now, as an exercise, try to prove the following on your own. If a closed hyperplane of a norm, now our main interest actually is in normal spaces. We are not really interested in pure algebra and vector spaces without any norm, okay? Because we need a topology on the space, okay, in this course. So if a closed hyperplane of a norm space separates two sets, then it separates their closures. This is a very useful exercise, and I think we asked it in the exam some time ago. And similarly, if a closed hyperplane strictly separates two sets, then it strictly separates their closures. Okay, try to prove this exercise on your own to really test your understanding of these concepts. Okay, and now we can formulate our problem at last. Given two disjoint convex subsets of a normal space C, can we separate them always by a closed hyperplane? And when can we strictly separate them by a closed hyperplane? Okay, two questions that we are. So let me give you some elements. If E is finite dimensional, then every hyperplane is automatically closed. Okay, because the linear map is automatically defining it as continuous, so it's closed. And we can always separate two disjoint convex sets by a hyperplane. Okay, this is proved in exercise 6 of this chapter. Okay. However, we can give a counterexample in infinite dimensions. If the space is infinite dimensional, or we give an example of an infinite dimensional vector space where we cannot separate two disjoint convex sets by a closed hyperplane. Okay, so this is explored in exercise 6-7. Okay, so in infinite dimensions, one should be more careful actually. Okay, so we have this counterexample shows that we have to put an extra assumption on the sets other than the fact that are convex and disjoint. Okay, we need an extra assumption, and this is the object of the next theorem, the Hahn-Banach theorem, first geometric form. So again, we have two disjoint, of course not empty because we are not interested in this trivial case, so not empty, convex and disjoint. Okay, and this is the extra assumption. One of them is open. Then yes, the answer is yes. We can separate them by a closed hyperplane. Okay. So in order not to make this video very lengthy, I think I'll stop now and give the proof in the next video. Okay. So thank you for your attention and see you very soon. So in the next video, I'm going to prove two preliminary lemmas. One of them is a particular case of this theorem. Okay. So see you soon.